What we had talked about last time in the discussion of streams were the fundamentals of streams, the common aggregate operations, and I'd given you an overview of splitterators. And if you recall, splitterators were the part of the Java stream that takes a data source and splits it up into chunks. What we're going to do now is we're going to talk about how you terminate a stream, which in some sense is the inverse of splitting the stream. So splitting is what takes the source and turns it into chunks to be processed by the stream, by the aggregate operations in the stream. And then terminating a stream is what happens at the end of the stream. Every stream has to finish with a terminal operation that yields a non-stream result. So if you think back to our simple example we talked about before, where we had the characters in Hamlet, which would then be filtered out by whether they started with H, we would then capitalize them, sort them. One thing we could do at the end is print them out. And a way we could do that is by using the forEach operator, which is a terminal operator that takes a stream as input and then does not return a stream as output. So it's a non-stream operation. So forEach is a good example of a terminal operation that has no value returned. It's only having side effects. So the purpose of forEach is just to have side effects. As you'll see, there's other kinds of terminal operations that return a result, and it's often called a reduce operation. And as we'll see in a second, there's two general categories of reduce operations. There are single primitive results where you give back a number like 42, and there's also something where you get back some kind of collection using the collect operation. Let's first talk about how you terminate a stream using operations that have no values at all. They only have side effects. So this example comes from my EX12 folder in my GitHub account. And as you can see, it's the test called run forEach. And it has a stream that does all the things we talked about. And at the end, we simply call forEach. And as the name implies, forEach performs that designated action, in this case printing, on each element in the stream. And forEach has semantics that says, I'll let the stream implementation figure out the order, the best order to do the stream values in. You, programmer, have no control over it. Here's an example where we can demonstrate the fact that the action passed to forEach has a side effect quite nicely by having a results array list, which is a list up here at the top. And what we're going to do is for each element in the stream that survives all the aggregate operations or the intermediate operations ahead of it, we're going to go ahead and add that element to the results list. So you can see this will add the element at the end of the list. This just demonstrates that you can have side effects. forEach intentionally is designed to have side effects, which is a little bit unusual because most of the operations in streams are not intended to have side effects. Be careful when using forEach, however, with a parallel stream. So if you were to try to use this in a parallel stream, then chaos and insanity would result because we'd be calling add on this array list, which is not synchronized. So array list is not synchronized, which means it's intended to only be called in one thread of control. If there's more than one thread of control, then you'll have race conditions and memory visibility problems and all that good stuff. So you wouldn't want to do this. There's much better ways of doing it. There are other operations that we'll see. There's things like forEach ordered, which orders the results. The other terminal operations return the result of a reduction, and we'll talk about various of them. So for example, the collect method is used if you want to give back some kind of collection containing the results of what is in the stream. So this is what's called, we'll talk more about collect shortly, but it performs a mutable reduction on all elements of the stream using some type of collector. What the heck does that mean, some type of collector? What is a collector? Well, a collector is basically a data structure that performs reductions. So it could accumulate the elements into various types of collections. It could summarize the elements according to different criteria, like what's the highest value, what's the lowest value, what's the average value, and so on and so forth. Here's an example of a very common collector called toList. This is actually built into the Java streams class library. So toList will take whatever is coming through the stream, and it accumulates the stream elements into a list, which is implemented under the hood as an array list. You'll have an array list's worth of elements that'll be stored in the results here. Here's a similar approach using a different data structure. This uses toSet. toSet is also a factory method that knows how to create an accumulator, a mutable result container, as it's called, which accumulates the stream elements, except it stores it into a set. What's the difference between a set and a list? A list can have duplicates, whereas a set does not. Yes? Oh, good question. Does this work with parallel streams? This will actually work just fine with parallel streams. And that's because if we were to turn .stream to .parallel stream, the way that the collector works is it handles the parallelism correctly when it collects things. I'll talk more about that later. That's a good question. Actually, your question is perhaps more profound than you imagine, and that has to do with how sets are merged together. So this will function correctly. It'll give you the right result, but its efficiency may be not what you'd expect. And I'll talk later about two different types of collectors, concurrent collectors and non-concurrent collectors. This, in this particular case, would be a non-concurrent collector. So it'll work properly in a parallel stream, but it might not give you the optimal behavior. And we'll talk more about that shortly. Here's yet another type of collector. This is called it's a map collector. And so the toMap factory method will take the elements in the stream and turn it into a map. And in this particular case, the map we're going to have as a result of this is going to be a mapping of the character's name, like Hamlet, and then the length of the elements in the character's name. How many elements are there? So in this particular case, what we're going to do is we're going to make a map, and the character's name will be used as an identity function to be the key, and then the value will be the length of the character name. And if two characters have the same name, again, for those of you who remember Hamlet, for some strange reason, there's two Hamlets in Hamlet, there's two Fortinbrasses in Hamlet, and so on. And so if there's duplicates, then their lengths will be summed together. So that's the merged duplicate entries. The lengths will be summed. So this is going to create a hash map that will have the character name followed by the number of letters in the character's name as a number. There's some other really cool collectors. This one's called a grouping by factory method that makes yet another kind of collector, which is also a map, except in this case, you can define a few extra things. If you take a look here, you'll see that we ended up only being able to use a hash map. Whereas with grouping by, you can actually indicate what kind of map you want to be used as the implementation. So in this case, we're going to use a tree map. And a tree map, as the name implies, will store the elements in the map as a tree, which is ordered, whereas hash map would not be ordered. So what grouping by does, I think of grouping by as kind of like the silverware ordering tool that you put into your drawer, right, where you basically stick the big forks in one place and the knives and the spoons and the small forks somewhere else and so on. And so what we're doing here is we're grouping things into the map according to the key. So that's what it's called the classifier. It says how to put stuff into the map. And in this case, we're just using the identity function, so it just takes the values and uses those as the keys in the map. We can indicate what kind of map we want. We want a tree map in this case, using a factory supplier. And then there's also this thing called a downstream collector. So after we group things according to the identity, then we go ahead and put the values, and in this case, we're going to sum up the lengths together in order to make the values here. So it'll add them all together. This is called a downstream collector. You can read more about downstream collectors here. Here's yet another cool thing you can do, just another example of how to use streams. Here we take a string. We might just have a string with Horatio, comma, Hamlet, comma, Laertes, comma, Gertrude, comma, Claudius, whatever, all the characters in Hamlet, just as one big string. And then we can use the regular expression features in Java to say, compile me a regular expression matcher that uses comma as the separator between elements in the string, and then split this string into a stream using comma as the thing to figure out what will separate each element in the stream. So that'll be, you know, Hamlet or Horatio, Hamlet, and so on. Any questions about that? So another really cool thing you can use with streams is to just create a regular expression splitter that splits stuff into streams. And then, as we did before, we can collect things into a tree map or some other kind of map if we want to. So those are examples of collections that are returned by collect. Collect is a very, very common way of handling things in Java for stream terminal operations. That's the most common one. There is another kind of reduction operation, however, which is used for primitive values, and this is called reduce. So if you want to be able to return a collection, then collect is what you use. Conversely, if you want to be able to return a single value, then reduce is what you use. So in this particular case, we're going to end up with a map, which is the characters, the character names and the length of each name. And down here, we're going to figure out the count of all the characters' name lengths added together. That's what we're trying to do. So we're going to end up with count of name lengths. And how we do that is we take our matching characters map, which is what we have up here. We convert this in such a way that we're only interested in the values. We don't care about the keys. We just care about the values. So we're going to have a, basically we're going to get the values collection out of the map. We convert the values collection into a stream. So now we have a stream of longs. And then we're going to go ahead and reduce that result into a final result. And how we're going to do that is we're going to say, start this with the initial value of 0. And then for every element in the stream, actually every 2 elements in the stream, add those 2 elements together and come up with a reduced value. And this happens over and over again until we've reduced the entire stream of longs into a single result, which was the result of adding everything together. So basically, it's going to sum the lengths of all the character names in Hamlet. And the way this works is you give an identity function, or sorry, an identity value, which in this case is 0, because 0 is the identity value for addition. And this not only serves to start out the accumulation with a default value, which is the initial value, it also serves as the final result if the stream is empty. So if for some reason we had no characters in our stream that survived all the filtering and other things we did, we'd still end up with a meaningful result. This lambda expression is what's called an accumulator. And it's basically a stateless function that combines 2 values into a single, immutable, reduced value. So it just adds the 2 things together. Here's another version of this. This is the 3-argument version, and this is meant to be used with parallel streams. And this is what we often call a map-reduced version. So this is going to perform the operations in parallel, and this is then going to be used to merge them all back together when we're done. It turns out that this is such a common thing, adding everything up in a stream, that there's actually a single terminal helper method called sum that will do all of this stuff. So if you don't want to have to write that code, you can simply write this code, and that'll sum everything up and give you a single result. Some of these things will come in handy later when we do other assignments where you get to do summing of things. So the thing to remember, and this is the question that was asked a little bit earlier, collect and reduce are terminal operations that work seamlessly with both sequential streams as well as parallel streams. So it doesn't matter functionally whether the stream you have is a parallel stream or a sequential stream, you'll get the same results, but it might make a difference in terms of how well it works depending on which type it is. And we'll talk more about that later when we talk more about collectors. Okay, so that's the end of part 4.